So example 1, now that we've laid some groundwork in probability, goes back to listing the sample space as a reminder that the sample space is where we're always going to start with our probabilities. So example 1 says, list the simple events associated with each experiment. And A is a nickel and a dime are tossed, and the results of a head or tail is recorded with each coin. So our sample space would be a head with a head with a tail with a head, or a tail and a tail. So head on the first coin, head on the second coin, head on the first coin, tail on the second coin, etc. So we've done that before. It should just feel comfortable at this point, of course. Okay, part B says an opinion poll is conducted among a group of registered voters. Their political affiliation, whether they're a Democrat, Republican, or an independent, and their gender, male or female, are recorded. So our sample space this time would be, you could be a Democrat and a male, you could be a Democrat and a female, you could be a Republican and a male, or a Republican and a female. You could be an independent with a male, or an independent with a female. And there's our sample space. Example 2. So it actually gives us a population distribution. It says the percentage of the general population that has each blood type is shown in the table below. Determine the probability distribution associated with these dates. So here's the blood type. And you can either be A, B, AB, or O. And then the percent of the population. You could have 41%, 12%, 3%, or 44%. So there it is as a relative frequency. All we're going to do is translate it into a probability distribution. So we're going to list an event, and the event would be either an A blood type, a B blood type, an AB blood type, or O. And then instead of the population percentage, we're going to list it as a probability. Now, luckily for us in this particular example, because they're listed as percentages, we can just roll those over to our probabilities. In other words, this is saying 41 out of 100. So that would be 0.41. B would be 0.12. C would be 0.03 or 0.44. You can also list them as percentages, but I think they carry more meaning this way, just to make that translation between a frequency distribution and a probability distribution. Okay, our next example goes to a larger audience and looks at their blood type. This is example 3. So this time, blood types, and again, we have A, B, AB, and O, and the number of people. This time we had 645, 160, 43, 652. And it does tell us that altogether we have a total of 1,500 people. So we're going to make a probability distribution. This is part A. So again, the labeling inside the chart is changing to event. The events are still the type of blood. So A, B, AB, and then O. Do them in the same order. And then down here, we're going to have the probability. So we know that there were 160 out of 1,500 people that had type A blood. So the size of our specific event is the 160. The size of the sample space is the 1,500. And if we take 160 and divide it by 1,500, we'll end up with 0.107. So this is 0.107. For B, it's only 43 out of the 1,500 people. So we'll take 43 and divide it by the 1,500. Again, size of the sample space is 1,500. The size of this specific event is the 43 people. That comes out to be 0.029. Whoops, I got off. Sorry, I really got off on that. Let's translate those across. That was me just not reading correctly. Let's try that again. So type B was the 160 out of the 1,500. Which was the 0.107. 0.107. You're probably screaming at me on the internet there. This is the 43 out of the 1500, which came out to be 0.029. Okay, we'll backtrack. A is 645 out of the 1500. 645 divided by 1500 comes out to be 0.43. And then finally for type O, the most common, 652 out of the 1500, which comes out to be 0.435. And if we've done everything correctly, when we add these together, we'll end up with 1. Now, because we did some rounding along the way, it will be close to 1. So 0.107. I'm going to add them as I have them on the board. 0.029, 0.435. Comes out to be 1.001. So essentially, 1. And that's how you make a probability distribution. Now, part B is asking, now that we have that, what's the probability that a person selected at random has type A blood? So the probability that we have type A blood is this 0.43. So ideally, once we have the distribution, answering the questions is very straightforward. Part C is asking, what's the probability that a person selected at random has type A or type O? So the probability that you are A, and because it says the word or, we know that or is a union, type O blood. So we're going to take the type A blood and add to it the type O blood, which was 0.435. And together, when we add those, we'll get 0.865. So notice that the simple events themselves were added together. We're looking for their union, and we can add those together. So the probability of an event, we can come in and finally formally define it. So the probability of a specific event is equal to the number of ways the event E occurs all over the number of sample points in the sample space. So another way of thinking about this is the number of ways that E can happen over the number of ways that S can happen. And that's what we did in the previous example. We looked at each of the individual blood types and divided them by the total number in the sample space. So example 4 asks us, according to MediaMark research, during a certain year, 84 million out of 179 million adults in the United States corrected their vision by using either prescription eyeglasses, bifocals, or contact lenses. So what's the probability that an adult selected at random from the adult population uses corrective lenses? So the size of our sample space is always the larger of the two numbers. That's 179 million. And we know that 84 million of them, sure enough, went ahead and used corrective lenses of some type. Now, the million part of this is going to divide out. So we just need to take 84 and divide it by 179. You are more than welcome to leave your answer as a fraction, but make sure as a fraction, it is a reduced fraction. In this case, it's easiest just to go to the decimal. So the probability that a randomly chosen adult wears corrective eye lenses is 0.469. And this was in whatever year the MediaMark research happened in. Okay, let's try one more on this part of the videos. According to the data obtained by the National Weather Service, 376 of the 439 people killed by lightning were men. So 376 men, 439. So out of 439 that were killed by lightning. And that was between 1985 and 1992. So part A wants to know, what is the probability that a person killed by lightning is a male? So the probability that that person is a male is simply going to be that 376 over 439. 376 divided by 439 comes out to be 0.856. What's the probability that a person killed by lightning is female? Now, we have a couple ways of doing this. I'm going to treat it as a complementary event, meaning the only thing that can happen here is the person killed was either male or female. No other possibilities are out there. So I'm going to treat this as 1 minus the probability that that person was a male. So we'll do 1 minus 0.856 to figure out the probability that the person killed by lightning is a female. And that comes out to be 0.144. So for the first time, we can truly see the idea of the complementary events, right? You're either male or female in the outcomes here, and they're complementary.